I want to do a brief review of what we did. And what you'll find here is that we started with acceleration, and we said that acceleration was a vector. It has both magnitude and direction. The way we define magnitude, which is we write A delta V over delta T, what this equation tells us is that how quickly velocity changes. And what we tried to say here is that the way we measure magnitude in everyday situations is we measure the strength of your body's motion. If you stop quickly, and what we mean by quickly is that you stop over a short time interval, your body moves strongly in the forward direction. Because it's strong, we then say that that's a large acceleration. Why is it a large acceleration? Because a little bitty time in the denominator gives you a large acceleration value. On the other hand, if you stop slowly, we typically mean that you stop over a long period of time, your body only slightly moves forward, and therefore that slight motion tells you that you have a small magnitude of the acceleration. So when I look at the acceleration equation, I have a big time interval, and therefore in the denominator, and therefore a little tiny acceleration. Then we started talking about the direction. The direction is always opposite to your body's motion. So if you're slowing down, as a car is going to the right, what you're finding here is that your body has a tendency to slide in the forward direction. By our definition, the acceleration is in opposite the direction of your body. So the acceleration is opposite to the direction to the velocity. This is what we mean by slowing down. If we're speeding up, our bodies get pressed into the seat. So therefore, the acceleration is opposite to our body's motion. This acceleration is in the same direction to the velocity. We define the direction of motion, the velocity, to always be in the positive direction. So you can see here that what we mean by opposite acceleration, it's opposite to the velocity. What we mean by the same as the velocity, it's in the same direction. So if I add these to motion diagrams, if I have constant velocity, note that that velocity vector does not change. So therefore, that tells us the acceleration is 0 as I move to the right. On the other hand, if I am speeding up and my vectors are getting longer and longer, then we say that the acceleration and the velocity point in the same direction. Some people say that the acceleration is helping the velocity. It's not really acceleration, it's acceleration times time that is helping the velocity. And we'll get to that later on today, hopefully. And then slowing down means that our vectors are getting shorter. So in this case, the acceleration is working opposite to the direction of the velocity, and that's what's causing it to slow down. So in the language in physics, we don't use acceleration and deceleration. We only use the word acceleration. It's the direction of the acceleration that differentiates between speeding up and slowing down. So one example is if we are moving from Santa Cruz to Cabrillo and we are speeding up, that velocity, we might say, points in the positive direction. So if I'm speeding up, then the acceleration must be pointed in the same direction as the velocity. And since our velocity is in the positive direction, we call that acceleration positive acceleration and speeding up. Now, if we go from Cabrillo to Santa Cruz, the opposite direction, textbooks have a tendency to then say that from Santa Cruz to Cabrillo, that's the positive direction. From Cabrillo to Santa Cruz, that's the negative direction. If you play that game, which is not a game that I play, I would have just said that going from Cabrillo to Santa Cruz, that is the positive direction. So what I would say in this case then, okay, if my velocity is in the negative direction and my acceleration is in the negative direction, the fact that they point in the same direction, that is still positive acceleration, because you could see that the acceleration is helping the velocity vectors to get longer. This is still speeding up. Again, that's not my notation. I would have changed that. On the other hand, if I have velocity going to the right and acceleration going to the left, so by definition, I could see here is that the acceleration points in the negative direction, so we call that negative acceleration. So you must be slowing down, as up here on the motion diagram shows. On the other hand, if we played that game that the textbooks do, they would say, oh, the velocity is pointing in the negative direction. But if the acceleration is pointed in the positive direction, it does not matter. It's in the opposite direction. We still call that negative acceleration, even though the acceleration is pointed in the positive direction. What we mean by positive or negative is about how is the acceleration relative to the velocity. If it's in the same direction, it's positive, and therefore you always speed up. If it's negative, no matter what directions you define, then you must be slowing down. Then we started talking about the units of acceleration. And what we assume here is that we always assume that the acceleration is constant. So when I look at our definition of acceleration, it's this delta V that becomes the most important in defining acceleration. This time interval is always about 1 second. How much the velocity changes per unit time is what the acceleration is. But it's this delta V term that becomes important. So if I have positive acceleration, in other words, A is positive, then that means I'm putting a positive value for my acceleration direction. In other words, it's in the same direction as the velocity. So that means if I have this situation or that situation, it doesn't matter. It is positive acceleration. So therefore, the speed increases by 5 meters per second every 1 second. So if I start at rest, which means that at 0 seconds, my velocity at V0 is 0. But if my acceleration is 5 meters per second every 1 second, then what I'm going to find here is that after 1 second, my speed V1, which is equal to V0 plus delta V, we know that we're changing speed, then it's going to be 0.5. In other words, my speed has changed from 0 to 5 meters per second. After 2 seconds, I'm going to change my speed from V1 to V2. And you could see that I wrote V2 is equal to V1 plus delta V, which that delta V is in the acceleration. I'm going to get 5 plus 5, which is then 10 meters per second. So you're seeing the flow, how I'm increasing my velocity when I have positive acceleration. Negative acceleration does just the opposite. Negative acceleration tells me that it's opposite to the velocity, and therefore the speed decreases. How much does it decrease in this time? It decreases by 10 meters per second every 1 second. So if I'm slowing down, that means that initially at V0, I must be moving at a higher speed. In this case, I'm saying that this is 50 meters per second. But my acceleration is in the opposite direction, which means that I'm going to decrease this 50 meters by 10 meters per second every 1 second. So if I go to 1 second, then I'm going to have V1 equals V0 plus delta V. You could see I'm going to get 50 minus 10, which then gives me 40 meters a second. When I get to 2 seconds, then V2 is decreased from V1 by, again, minus 10 meters. So I'm going from 40 to minus 10 to 30 meters a second. That's why we call it positive and negative acceleration. Mathematically, it shows up that way. Furthermore, we can actually see this when we plot velocity versus time. So again, acceleration is a constant. So when I write it as a linear equation, the acceleration here is the slope of the velocity versus time, very similar to when we plotted position versus time. The velocity was the slope. Here, the acceleration is the slope. So if I have positive acceleration, I have a line that's positive, excuse me. If I start off at V1 and I have a horizontal line, this violet line, that means I'm not changing my speed. So here, this is telling me is that there's no speed change. That's what I mean by zero acceleration. The fact that I now have a slope, that means I now have speed change. And in this case, we have a positive slope. So you could see I'm increasing from V1 to V2. Now, according to how we write our acceleration equation, what we're seeing here is that delta V is equal to AT. So it's the acceleration here that's the cause of changing the velocity. So this height change on this curve, and you could see that it's a positive increase, means I have a positive acceleration because of the positive slope. So when I write this out, you could see that V2 is greater than V1 because I have a what? A positive acceleration. In other words, the velocity and the acceleration are pointing in the same direction. So when I look at my acceleration versus time curve, since we're only looking at constant acceleration, you could see my acceleration is above my A equal to 0 point. Now let's go to negative acceleration. Here, again, we have this line where we have no speed change. But as soon as I see a slope, then I have a speed change. But this time, you can see that V2 is higher than V1. The only way I could get down to V1 is if that line has a negative slope. And you could see here that delta V is then going to be equal to minus AT. So when I look at my linear equation, I get V2 is equal to V1 minus AT. By the way, that's exactly what we were doing right here. This is the exact same thing that we're looking at here. And we could see here is that V2 in this case will be less than V1. Therefore, my velocity is in the opposite direction of the acceleration. That's why in physics we call it negative acceleration. It makes mathematical sense. And then if I plot acceleration versus time, you could see that relative to the 0 point of acceleration, that is a negative acceleration. Okay, this is a fairly long review, but acceleration is a real issue for a lot of people. There's a lot of people that mix up acceleration and velocity, especially when we get to problem solving. And this is something that I see on the quizzes. So now we were finishing up example 2.2, and we were on part C, and we were drawing the corresponding acceleration versus time graph and its motion diagram. And here's what we did last time. What we said here is that we had this. If I divvy up my intervals with these dashed lines, I would say that 0.2 is not an interval. Why? Because I'm looking at the slope of the velocity. So if I look at from 0, 1, I have a negative slope. Therefore, I know my acceleration is negative. In other words, it's got to be slowing down. Or it's got to be moving in the negative direction, and you'll see what I mean by that. In this case here, by the way, I said slowing down. That was a mistake. Let me say that again. That was a mistake. I am not slowing down from 0 to 1. In fact, I'm speeding up. And I'll show you what I mean here in a moment. And so When I go from point 1 to 3, so I'm going through 1 through 2 to 3, that's a positive slope, so I have positive acceleration. Now, as I go from 3 to 4, you could see that I have a negative slope, so I have negative acceleration. So when I look at my curve, you could see that these were the accelerations that we talked about last time. So now let's draw our diagram. The first thing that you want to see here is that note, when I look at my curve, note that this is v equal to 0 at this point right here. Note that this speed, so if I call that v0 right here, v1 is greater than v0. Now note, I'm talking about magnitude. So if I compare the speeds, so that means comparing v1 versus v0, we're seeing that it's moving faster at point 1 than point 0. But it's moving in the negative direction. However, it moves in the negative direction. So if I'm moving faster, what that tells me then is that I'm going to have this. So before I draw the motion diagram, let's set the intervals here. So this is my point 0. And then this is my point 1 right here. Let's do it like this. This is my point 1. So when I look at this interval, what you're seeing here is that my velocity vector is moving in this direction, but my acceleration, I wrote acceleration, but my acceleration vector is pointing in the same direction. So you could see right here that I am speeding up. And then when I go to so then what happens here is that now I instantly, at point 1, what I'm starting to do here is that I'm starting to slow down. And what do I mean by I'm starting to slow down? You know what? I'm going to move this down. I need more space. So now what I'm going to do here is that I'm going to compare V1 versus V2, which is equal to 0. So if I'm moving fast at 1, what I'm seeing here is that I must be slowing down. So I am slowing down while moving to the left. Now, why am I moving to the left? Because note, the velocity is negative. The velocity is negative. So as I go to point 2 here, I am literally slowing down. Because look what we said. That if I look at my directions, this direction over here is my negative direction. This direction here is my positive direction. So when I look at my velocity, I'm still moving in the negative direction, but now my acceleration is in the positive direction. So when I get to point 2 here, what you're seeing here is that at point 2, you're seeing here is that the velocity at point 2 is 0. So what am I doing? Now note, right here, that means if I cross onto the other side, this tell them that if I'm above this, I'm moving right up here. Down here, I am moving left. So this tells me that when I get to here, I have now switched directions to right here, and this is now point 2. So what you're seeing here is that I now have a positive speed from 2 to 3. And so as I go all the way to 3 here, you're seeing here is that I've now changed directions and I have a positive acceleration. So I am now speeding up in the forward direction. Okay, I am speeding up in the forward direction. You know, I have a problem with what I'm showing here. And I realize that if you look at point 1 and point 3, note that I'm saying that that speed is 0. And what I'm doing here is that I'm not, in my head, I'm dealing with smooth curves, not instantaneous curves like this. So the speed is not 0 at that point. So I have a mistake on the graph. Points 1 and 3 do not have v equal to 0 values. Okay, they do not have v equal to 0 values. So instead of erasing it, I'm going to come in and I'm just going to exit to remind you that that is a mistake. So the only places where I have v equal to 0 is at point 0, 2, and 4. That is my mistake. So then when I get to point 3, that is not 0. All that means here is that I'm going to start to slow down. So if I look at point 4, you can then see that if I compare V3 versus V4, which is equal to 0, you could see here is that now I'm going to be slowing down while moving right. In other words, because my velocity is positive, I have to be moving right. So when I look at this point here, 4, what I'm seeing here is that I continue to move right here. God, I keep writing acceleration with this color. And then my acceleration is in the opposite direction, which then means that I am slowing down. So if I was to look at what's actually happening in this curve, you can actually see that I can come in and I can do this here. In this situation, my velocity in this interval here, my velocity is in this, my velocity and my acceleration are in the same direction, and therefore I'm speeding up. Here, my velocity and acceleration are in opposite direction, and therefore I slow down. And then when I get into this interval, I'm seeing that I'm now speeding up because they're in the same direction, And then finally, in this interval, I continue to move in that direction, but now you're seeing that the acceleration has changed direction. So that's what this motion diagram looks like. Now note that, again, I apologize for this mistake with my points 1 and 3. Yeah, that was just a screwy thing that I did. Okay, I am done with this example, and now we want to get into kinematics. So now we want,
Carlos,
yes,
at point 2, should that also read v equals 0 then, rather than v is greater than 0? Or is it
at point 2?
at point 2 on the blue graph?
I actually meant to write that as 0. That is 0 right here.
Okay, okay, good.
Okay.
Thank you.
Just because that's the line that defines that as 0. Okay, thanks for the remark. So now, here we go. We're going to look at kinematics. And this is the toughest part of the chapter. Okay, so what we're looking at is we're looking at one-dimensional motion with constant acceleration. And kinematics is the math. So when I look at the one-dimensional motion with constant acceleration, we are now looking at mathematically solving for the motion. So our goal is not to derive the kinematic equations. But learn how to use them. I don't think you get anything by deriving them. And what we find here is that we really only have 3 definitions. Okay, so the variables are x, velocity, and acceleration. These are our only 3 variables, and we can take these and we can manipulate them. Okay, so what this tells us here is that if we know, not known, if we know position, velocity, acceleration, and time, then we can completely describe the motion of an object. And here is the kinematic equations right here. Okay, they look like this. This is very, very standard. These are in all textbooks, and this is the way they organize them. There are 4 equations, and the one you want to be careful with is this guy right here. This one is the most misused equation. If you know how to use it, then we can deal with this thing here. So your ability to use these equations and solve problems on your quizzes and exams, there's going to be 2 quizzes on motion, becomes crucial. So there are many techniques of how to do this. And what you gotta figure out is what works for you. You're an intelligent person. My job is to give you recommendations. Okay, and so as I give you recommendations, you will find out that, you're going to take it or not. You got to figure out what works for you. But I'll try to give you an organizational scheme that, in my opinion, works very well. Okay, so here we go here. So my goal here right now here is that I want to organize and I guess, and for lack of a better word, sort of like digest these equations to help you solve problems. That's what it is. Again, there are many techniques. What works for you depends on what happens. My scheme depends heavily on the motion diagram. Okay, so what I'm going to do here is that I'm going to start listing what we find here. So the first thing that I want to do here is that I want to look at this in pieces here. So the first thing that I want to do is that look at these equations here. These 4 equations have 5 variables. But the kinematic equations each only contain 4 variables. So check that out. If you look at the first one, you could see that there's V initial, A, and T. Note that something is missing from the first one. What's missing? It turns out delta X. Delta X is not there. Okay, so what are my variables here? So if I look at my variables right here, there's delta X, V initial, A, T. So you can see that the first one, this guy right here, is missing delta X. Okay, and then here, what's missing from this one? You could see here is that by definition, this is already delta X, but you could see here is that this is, I have V initial, I have AT, and I have delta X. What's missing here? What's missing is V, which is the final velocity. So what I've done here is that I've now created a scheme that helps you identify what's the missing variable. Not what you know, it's what you're missing. So here's my scheme. So what I do here is that I organize this information using what I call a data table. And in some cases, you'll have more. So how do I deal with a data table? Well, I list all 5 of the variables. And I typically write this as V2, V1, and T. So when I look at this, this is my data table. And so what this allows me to do here is that I can insert the known quantities from my motion diagram into the data table. You know, it's another way of just writing a quantity, sort of like what you know and what you don't know. This is a different way of organization, but you'll see that the data table is very important of how I set up what I call a kinematics table. So what you're seeing here is that each equation requires 4 variables. So if we know 3 of the variables, we can solve for the 4th variable. And what you're going to find here is that the 5th variable is not given in the problem. So as an example, let's look at the first equation. The first equation reads V equals V naught plus AT. So let's go look at that. So if I have V2 equals V1 plus AT, I would then set up my table something like this here. So let's say that what's given here is something like this. So the first thing that I would do here is that let's say that in this problem, we find that we're given V2, A, and T. So then what I'm going to come in here is that I'm going to come in and I'm going to say, okay, from my table, I'm going to say, okay, I know I've been given V2 and I put in its value. I know that I'm given A and I know that I'm giving time here. But what I'm solving for, I want to solve for V1. So then I come in and I put a question mark to tell me that's the variable that I'm solving for. But what determines the equation is the variable that I do not know. It's the variable that I do not know that explicitly tells you which equation to use. Because I don't have delta x in this thing, this is the unknown variable, it's not given, then that equation tells me what to do. And this leads me now to something that I call the kinematics table. And the key to using these data tables is this organization of the table that I have right here. This is the whole goal, is being able to master this equation here. So now look what happens here. So look at my data table. I immediately look for what's the variable that I don't have. I don't have x. So look what this thing. This guy right here tells me right away that this is the equation that I use. Look at this. If I don't have the final velocity, then this is the equation that I choose right there. This is what's guiding me to how to pick the right equation. It's this process right here. So now I now want to look at my problem-solving strategies and put all of this together and start applying this so we can start looking at problem 2. Okay, so now this is my last one here, and this is what I call my reasoning strategies, or my strategies, or my strategy for solving kinematic problems. Okay, and here it is. And it reads like this. So I wrote this in steps. Okay. Over time, sometimes these steps are not useful. It depends on how you operate. Okay. So step 1, draw a motion diagram or plot velocity versus time of the situation and interpret the question. So when I say a motion diagram, or if I say plot velocity versus time, that means it includes numbers. We haven't been doing that. We have to include numbers now. Step 2, define the direction of motion, the direction of the velocity, to always be positive. Why? Because if you calculate an acceleration and it's positive, then you know that you're speeding up. If you calculate an acceleration that's negative, then you know it's opposite to the velocity, so you must be slowing down. So once I do that, I now create a data table with the proper units of meters and seconds. Then step 4, I use the kinematics table to organize my thinking to select the correct equation. In other words, I'm looking for the variable that is not given in the problem. And then finally, step 5, I solve for the correct variable, and then I interpret what is going on here.